Okay, guys, so let's talk about discrete random variables. Remember, discrete is like a number, like a counting number. If you can count how many people walk into a store, that would be a discrete value. Um, and then if you have random, obviously that means just means that it's going to be a different, like it could be different on any given day. So, random variables, a numerical measure of an outcome of a probability experiment. Its value is determined by chance, obviously. Has a finite or countable number of values. Continuous random variable has infinitely many values. So I know that you could say maybe you might be able to make the argument, oh, the number of people walking into a store could be continuous. Obviously, there's a certain number of people that could walk through the door at any given day, but I think at the very most that number would be finite because once the day is over, you would stop counting and you'd say, oh, there were exactly this many people, and you would probably never get to infinity, no matter how many people, um, because they would eventually fill the entire store and you wouldn't fit any more people in there. So that's some reasoning behind that. Distinguishing between discrete and continuous. The number of A's earned in a section of statistics with 15 students enrolled enrolled as a discrete random variable because the value results from counting. If the random variable x represents the number of A's, then there are possible of x values, and this is more of like a binomial thing because you either got an A or you did not. The number of cars that travel through McDonald's drive-through, obviously that's also discrete because you can count how many number of cars went through it. And then finally, the speed of a car that passes by a straight trooper is a continuous random variable because the speed is measured. And so if they're using a radar gun, it might say you went 87.2 miles and maybe there's a little bit extra or something like that. And if the random variable is s represented by speed, then it's any real positive net value bigger than 0. I guess there would probably be a limit on this, but you'd have so many increments in between that. Would it be finite? Um, I don't know. I'll have to debate that with myself, but not here. So let's let P of x denote the probability that a random variable x is equals x. Big X equals x. Then P of x is equal to 1, so the sum of them adds up to 1. So all that means is every value for the probability distribution adds up to 1. And then all of the probabilities are between 0 and 1. So it says consider the following. Which of the following represent a probability distribution? A fails because this one's negative. I can tell you that right away. B might work and C might work. So let's look. If we add this all together, 20, 45, 55. Oh, they add 49. That's too big. So this one doesn't work. So this one probably does. 20, 45, 55. 55 and 31 is 86. And then 14 is 1. It doesn't necessarily have to be exactly 1. It could be it just needs to be very close to 1. So like 99.9 or 1.01. Just don't say 90. 0.9 is not a probability distribution. 0.9 would be a 90% on a test, and if you got a 90, you wouldn't run around telling everybody, "Oh, I got 100 on my test." If you got a 99, you'd probably say, "Hey, I pretty much got 100," or "I basically got 100. I missed 1 point." Suppose we were to consider a basketball player to shoot free throws. Let x be the random variable of shots made. So there are 0, 1, 2, or 3, and the probability table shows the following. This is the chance that they make 0 free throws. That's a 1%. They only make 1. That's 10%. They make 2. That's 3.8%. Or, I'm sorry, 30.8%, and then 51%. So this is simply a bar graph without the bar. It's just line and spacing. So it's just showing you the probabilities of what was shown on the table. This person's obviously a very good free throw shooter if 50% of the time they make 3 out of 3. I would think that means they're pretty good. I hope. Maybe I'm wrong. No, they must be okay, because if I shot it 3 times, I know I can't make free throws, and I would probably be the exact opposite of this. The chance that, what I mean is the chance that I make 1 is probably higher than the chance that I make 2 or 3. So consider the following. I collect a small sample from my stats. How many people live in a household? The responses are these, and we can construct a probability distribution. And so it turns out we can calculate the mean from this chart, and all you have to do is do x times the probability of each one. So there's a 2 times 0.2, 3 times 0.1, and so on and so forth. And so you can see that data here. 0 times 0.01, 0. 1 times 1, this was from the basketball example, 0.1, and so on and so forth. And it says compute this on the board. Obviously we don't have the board, and I don't, unless I think I was supposed to do it for the other one, but we're just going to move on. So I would basically do the same thing with these numbers here. 2 times that, 3 times that, and so on, and add them all together. That's what this says. And then I think we divide by the total number of frequencies. So, all right. So how to interpret the mean of a discrete random variable? The mean can be thought of as the mean outcome of a probability experiment if we repeated the experiment many times. So if the guy shot free throws 100 times, the mean value, he would make close to the mean in terms of shots. So if his mean is 2, then he averages 2 out of the 3. So he probably shoots them at a 66% rate if that's the case. But this says it's 2.4, so he probably shoots a little bit higher than 66, probably 70 or 80%. Since the mean of a random variable represents what we... Oh, I'm sorry, this is a new idea. We have expected value. Since the mean of a random variable represents what we could expect to happen in the long run, we call this the expected value. And so it says a term life insurance policy will pay a beneficiary a certain sum of money upon death of the policyholder. These policies have premiums that must be paid annually. Suppose an 18-year-old buys a $250,000 life insurance policy for $350,000. According to a poll, then the probability that they will survive is this. Compute the expected value. So, the probability that they survive, obviously, they're going to be a 0.9999, so they're going to have this 0.99 value, about 100%, times 350, because they're going to lose that, and we're going to do minus 350 because that's money out of their pocket that they're going to lose. And so then there is this amount of chance. If we do 1 minus this is the chance that they actually do die. And then they're going to be paid this much. Obviously, that's the 250 minus the 350 they paid for the insurance. And so the calculation comes here. And if we do this times this, and negative this times that. Oh, I'm sorry. We're looking at this from the insurance company's standpoint. That's why these are positive and this is negative. So there's an $84 expected income or profit, average profit for age 18 males. And so every 18-year-old male, they expect to make a profit of about $84. So that's how they make their money. Who Wants to Be a Millionaire? If you recall the game show, let's say you're on it and you have a $125,000 question with no lifelines. The question you get is the following. What Philadelphia Eagles head coach has the most victories in franchise history? And then they give you the 4 answers. If you get the question right, you'll get $125,000. If you get the question wrong, you'll fall to $32,000. And your third option is to walk away with $64,000. What would you do? Let's look at it mathematically. So the probability of guessing it right, let's say you don't know it, you guess it's 1/4. Probability you get it wrong, 3/4. And what is our expectation? So if we do 125,000, that's what you stand to win, times 1/4. And then you do plus 32,000 times 3/4, what you'll drop down to. Your expected value is $55,250. and this is less than 64,000 to walk away with. So obviously our decision here would be to walk away because this expected value is less than this value here. But what if we had a 50-50 where we take away two of the wrong choices? Well, then now the choices are these two people, Greasy Neil and Andy Reid, who you might know. And so 1/2 times this and 1/2 times 32,000 gives us 78,000, which is greater than 64,000. So at this point, we decide that it's actually worth it to make a guess, even if we get the wrong thing. It's actually more beneficial more times than not. You stand to win more money. And so if you got it right, you'd say Greasy Neil, and you would have won the money on that. So standard deviation using the calculator of a discrete random variable. So you're going to put it in the table. L1, this is x. L2, this is p of x. And then you're just going to do your 1-var stats. Frequency list 1, frequency list is 2. Sorry, list is 1, frequency list is 2, and then calculate it through the 1-var stats. And that will get you through discrete random variables. I hope this is helpful. Let me know if you need more help. Thanks.